before we launch that slide on there, on our previous discussion that we emphasized on the glycolytic process, we arrived at a point where ATP was produced, and then we produced the pyruvate acid, and we are about to get into the Krebs cycle. Quickly, we rush down to our slide to have a look at the Krebs cycle, glutathione and G6PD deficiency. So I just copied the process that we did for glycolysis and pasted it here. We don't need this. What we need is to launch our next slide. So this slide basically represents our coenzyme A. So I've put here coenzyme A structure, not coenzyme A structure. Sorry about that. It's a coenzyme A structure. So what is the structure of a coenzyme A, and what is actually a coenzyme? So when we talk about a biological coenzyme is a non-protein, but it's a biological molecule mostly made of vitamins like flavin. So these vitamins carry electrons, protons, atoms, phosphate side groups, and these are carried on a temporal basis. They are transient carriers, and they carry them as a way to trigger a biological process, meaning they activate an enzyme to begin a biological process. The biological processes by which enzymes are involved include the glycolysis pathway, the Calvin cycle, which is in plant photosynthesis. We also have Krebs cycle that we are about to discuss, as well as the glutathione pathway, and all these require enzymes. Now, looking at them, because we have already explained that coenzymes are transient or temporal, meaning they can exist in different states. The two main states that we have for coenzymes to exist are the reducing and oxidizing states. So we call them reducing agents and oxidizing agents. And just to give you a heads up with some clue about this that I'm coming to explain to make it more easier, imagine an electrical system where electrons flow in a wire. So they try as much as possible to get earth wire and all that, so that overflow of charges will be directed onto earth. In a human system, the best way is that these are available because this is a biological system, and of course during metabolic processes there should be electron transfer, and of course this electron transfer should be balanced. There should be a system where electrons are received and unleashed as much necessary as possible to keep the body balanced with charges. These coenzymes are responsible for this very powerful balance within the human body. And looking up here, as you've seen, two molecules of electron transfer would require one proton or H+. This is not a strict requirement, so depending on the particular chemical system, and this is the discussion we are having here, is a biological electron transport chain. So circumstantially it may differ. In some way, when there is two molecules of electron transfer, it can cause an influx of about 10 protons to move around the mitochondrial matrix and cellular membranes. In some other chemical systems, two electrons could cause the influx of 4 protons and all that. So depending on what system and what circumstance it is and what reaction is occurring in there. So pertaining to this discussion, that's what we are going to use. What we mean by reducing agent and oxidizing agent. So when you look on here, the two sides that I've arranged, if you look carefully, you've got those that have an H in the end, this and that, and those that have a plus in the end. And of course you haven't forgotten your electron arrangement on orbitals. And of course when an atom loses an electron, it becomes oxidized or charged. The charged state, which is an integer, theoretically is what we call an oxidized state. And when we have an electron being received by a particular coenzyme, we say it has been reduced. What do we mean by them? It is the electron transfer. So I discuss this as a hunger and full system. So when you are hungry, it means that you have lost energy, and this is a high electronegative electron or a high charged electron that we are speaking about. So if this is nicotinamide adenine dinucleotide phosphate, and here it has the charge and we call it oxidized. Oxidized means it has lost its electron. It means it is in a state where it can receive electrons. So if this nicotinamide adenine dinucleotide phosphate oxidized, which has the H+, receives an electron, it becomes nicotinamide adenine dinucleotide phosphate reduced. So we can draw this onto that. I'll just pick let me pick a red one and draw it onto that. And of course, when nicotinamide adenine dinucleotide, which is oxidized here, receives an electron, it becomes reduced, and this is the state. So we match them onto that, and of course this is the flavin adenine dinucleotide. This is an oxidized state and it becomes reduced. And this is glutathione. This is glutathione oxidized, and when it receives a proton or electron, it becomes reduced. So the discussion we can make here between oxidizing group, that is the oxidizing state of the coenzymes, and the reducing state of the coenzyme is that in an oxidized state, it is in a state where it can receive electrons. In a reduced state, it is in a state where it cannot receive electrons, but it can donate electrons. And in the reverse definition, the reducing agent, it is in a state of reduced because it has got this electron, meaning it can donate onto others that are oxidized to cause them to become reduced. So if you have the nicotinamide adenine dinucleotide phosphate reduced, it can donate its electrons onto an oxidized atom or molecule and cause them to be reduced. So reducing agent cause others to be reduced, and when they reduce others, they themselves become oxidized. So note the balance. So what you have to understand between this is that in between these is a redox reaction. When we say a redox reaction is a type of chemical reaction in which state there is a co-occurring transfer of electrons between two. So one is receiving and the other is donating at the same time. That is what we mean. So it means in that state of redox reaction, one is becoming reduced and the other is becoming oxidized. That is basic understanding of a redox reaction. So when you say this state is a redox reactivity, you should be able to conform to that. Once you understand this, we are done with the rest. Let's go on. We know that there are coenzymes. So when we hear about acetyl Co-A or coenzyme A, this is what we are talking about. And the next thing we know about coenzymes is that coenzymes have got either electrons, protons, atoms, phosphate groups, and all these that are attached to them that do trigger an enzyme to begin a biological process. So when you look at the structure of the coenzyme A, it has got a sulfhydral motif, which is this SH, and this SH is mostly in between every compound that reacts with a coenzyme A, and it's got a phosphorylated ADP, and I told you they have phosphates attached to their system. This is the pantothenic acid in the form of vitamin B5 that is also part of its structure. And then lastly, we have the mercaptol ethyl amine tail, and this mercaptol ethyl amine tail breaks off anytime it's undergoing a reaction and it doesn't form part of the resulting compound. Now we can move on straight forward onto our Krebs cycle. Great. If you do remember our glycolysis, the end product of our glycolysis was production of pyruvic acid, and this pyruvic acid is the derivative that begins the Krebs cycle. And of course, you should know that 1. Glycolysis is an anaerobic process. 2. It occurs within the cytoplasm, and 3. It is not the maximum ATP produced in this oxidative process of ATP production in the human body, but rather the enormous amount of ATP is produced within the mitochondrial matrix, and therefore this pyruvic acid has to cross a borderline. And it is not just one borderline, but 2 borderlines. So the mitochondria has got its porous outer mitochondrial membrane and the inner mitochondrial membrane, and the pyruvate crosses both, and inside there about 28 to 34 ATP is produced in this respiration, which is an aerobic process of metabolism of glucose. Now let's see, we have transferred this pyruvate acid across this membrane onto here, and we have this pyruvate on here in the mitochondrial matrix. Inside here is where we have to understand the reaction of NAD and NADH. So it is inside here that we have to understand the meaning of coenzymes, the functions of them, and how they play a vital role in a biological process. Now let's move on. We have got the pyruvate present within the mitochondrial matrix. If we want to produce a functional group like acetyl group out of the pyruvate that we have got in here, look, let me show you. This is the functional group that we want to produce. A methyl group binding to a carbon that is double bonded to an oxygen and with a dash, meaning it is ready to bind. That makes it a functional group. This structure is similar because you have CH3 here, CH3 here, carbon here, double bond and a double bond here. So what we are going to remove is this particular side of the pyruvate. So we have to get rid of this. I wanted to draw it. So you have to get rid of it in order to produce an acetyl group. These are the interesting mechanisms in here. There are enzymes present to do this function. If you look very well what we want to remove, this C double bond O and the C dash O is carbon dioxide. So there is an enzyme called pyruvate decarboxylase. This pyruvate decarboxylase is responsible to remove that portion of the pyruvate to make it possible for us to get the acetyl group. So this portion will be taken care of by the pyruvate decarboxylase. It will be left with a hydrogen ion, that's we call it a proton, that has to be removed, and we've got a dehydrogenase, a pyruvate dehydrogenase enzyme present in here to do away with the hydrogen on here. So the process by which a pyruvate is converted into an acetyl functional group is by a decarboxylation and a dehydrogenation of the pyruvate in order to obtain this acetyl group. One thing you should note here is that this carboxyl group, which is the functional group of the pyruvic acid, has been taken off, and this is the alpha carbon. Anytime a functional group is directly taken from the alpha carbon, the remaining derivative product is not stable, and we call this second carbon an alpha carbon. The whole reason is that the next carbon following a functional group is called the alpha carbon. The unstable product that will be produced after decarboxylation is converted into a stable product by the E1, which is the pyruvate dehydrogenase, and that product is hydroxyether, and hydroxyether is stabilized by TPP. So TPP is a coenzyme for pyruvate dehydrogenase, which will produce the hydroxyether, and hydroxyether will form a complex with TPP. So it's normally called hydroxyether TPP complex. This will be transferred onto the next enzyme, which is E2. So I can just quickly circle on here the E2. So note the E2 enzyme is called dihydrolipoyl acid transacetylase. So this E2 enzyme, just for us to be very quick on that, it has got a coenzyme A and a lipoic acid. So coenzyme A and lipoic acid, and note here the most important of all the discussions that will get us back into this reducing agent is the lipoic acid S-S, which means a disulfide bond. So the disulfide bond here in the lipoic acid is a side chain, let me put it that way. It's a coenzyme which forms a part of the enzyme here, and it is the side that interacts with the hydroxyether that is being transferred from E1 onto E2. And remember this, once we are delivering this compound onto the disulfide bond, an electron will be released, which means there will be a proton, which is H+. Now the disulfide bond is broken. We are having one H and one S. What we have now is what we call the sulfhydral bond. During this electron transfer, the hydroxyether that was from here, the E1, to the E2, and of course it is a hydroxyether TPP complex that was transferred to E2 here, is now converted into the functional group acetyl. This acetyl interacts with the second sulfur within the sulfhydral bond, the second sulfur within the sulfhydral bond, and in the electron transfer and the creation of a proton, which is an H+, the two sulfur bond is now broken, and both of them are now replaced with an H, which means we have a 2H bond, which is a dihydrogen bond. So that's what I have got here, and in a second I will just circle it. Good. So quickly, now the acetyl group can now interact with the CoA, which is also one of the coenzymes on the sides of this enzyme E2, like I said earlier before, and therefore the acetyl group is now converted to acetyl CoA. So the acetyl group that we obtained earlier, where the disulfide bond was broken, interact with the next coenzyme on this great enzyme E2, and we obtain an acetyl CoA. But that's not where our interest is. If you would like to focus on here with me, remember that when it was lipoic acid disulfide bond, that was when it was able to receive the hydroxyethyl TPP complex. It means this disulfide state of the lipoic acid is the oxidative state. When it says it is in an oxidative state, it is in a state of reception, receiving something. But now it has been replaced with a 2 hydrogen bond, which is a dihydrogen bond. And now the name of this coenzyme or this motif on our enzyme is no more lipoic acid, making it a dihydrolipoamide. So I will circle this dihydrolipoamide or dihydrolipoamide, however you will mention it. So it means that now we are in a reduced state. A reduced state means that the surfaces are occupied and it cannot receive any other complex from E1. All that the next step does is to transfer the whole reaction from an E2 enzyme to an E3 enzyme. The E3 enzyme is what we call the dihydrolipodehydrogenase, and it has got FAD and NAD as a coenzyme. Now we are landing. FAD and NAD was part of the discussions we made before we jumped up onto the next slide here, where nicotinamide adenine dinucleotide phosphate, when it is reduced, it loses electron and it becomes oxidized. Quickly we go back. This is flavin adenine dinucleotide, FAD, and this is nicotinamide adenine dinucleotide, NAD. Both of these are in their oxidized state, which means they are in a state of reception, in a state to receive. FAD is the main coenzyme for E3. Now, when the whole reactions here transfer from E2 to E3, we've got the dihydrogen bond over here. So now the dihydrogen bond will be transferred in the E3 to the FAD, and this is our FAD, a coenzyme. It transfers the 2 hydrogens into FAD and it forms FADH2, which is a reduce. So now it reduces the FAD with 2 hydrogens or electron transfer, making it obtain a proton that changes its state from an oxidized state to a reduced state, FADH2. However, the most stable electron balance is NAD, and then the FADH2 is being catalyzed by the help of this enzyme E3 to transfer the protons or the H2, and this electron balance is now between FADH2 and NAD, and then it converts the stable or oxidized NAD to NADH. Now electrons are balanced to the most stable coenzyme, and this NADH awaits for the next metabolic activity that would require an electron or a proton transfer for it to begin. And now what we can talk about is that the dihydrogen bond is now taken off, allowing the disulfide bond to regain its state, making the lipoic acid in a state of oxidation or oxidized to receive the next hydroxyethyl TPP complex. And don't forget, I have circled this S. Anytime you see the CoA, you have this sulfur bridging between the functional group here. It is because during the time that the acetyl group was interacting with the sulfhydral bond, we still had the sulfur group. So the S here is because of the sulfhydral bond during the conversion of acetyl and then its interaction with CoA. Now we have our acetyl CoA ready to enter into the 8th enzymatic step, which we call the tricarboxylic pathway or the tricarboxylic cycle. People also call it the citric acid cycle, and I know it as the Krebs cycle. So we've finished portion of it and we are about to enter into the cycle. We wouldn't go through the cycle, just want you to know the initiation into the cycle, and the rest is about electron balance, transfer of protons, condensation, and ATP production. So it goes this way. You've got acetyl CoA and we've got oxaloacetate, and this reaction is a condensation which is facilitated by the citric synthase, and then it takes this for formation of citric acid, which continues with the cycle round, and so much energy ATP is released on here. And just like I said earlier, it's about 28 to 34 ATPs producing cycle of glycolysis in the